Okay, so Unit B, redox. We started out by talking about what is oxidation and what is reduction. So remember that oxidation is the loss of electrons, but reduction is the gain of electrons. You have to remember that because basically every question involves oxidation and reduction somehow. So maybe you liked oil rig, maybe you liked Leo the lion says grr, oil rig, oxidation is loss, reduction is gain, or loss of electrons, oxidation, gain of electrons, reduction, whatever you're going to use, you should have some way to remind yourself of this. They take place simultaneously, so at the same time, which means if something lost electrons, something else has to gain them. They have to go somewhere. So it's a redox reaction. And very frequently, there's a question that simply asks you to identify which of the following reactions are actually redox reactions. So remember, not double replacement. The other types of reactions that we saw in the first unit and this one, like formation, decomposition, combustion, and single replacement, would all usually classify as redox reactions. In a formation reaction, you have elements going together to make a compound, and elements have 0 as their oxidation numbers and compounds don't, so that one is an easy one to identify. Decomp is just the opposite of that. Combustion always has oxygen as an element going to oxygen in a compound. Oxygen will always be the oxidizing agent in a combustion reaction. And then if there's a single replacement one, it would be as well. Sometimes, though, the reactions aren't just those kind. So I always tell people to check oxidation numbers. If you can find an oxidation number that is changing, and the question is only asking you to identify, is this a redox reaction? If one of them changed, another one has to as well. So if you can find one that's changed, you can be certain that it's going to be a redox reaction. Do you guys want to ask anything about that? Okay. So from there, we go to the agents. Oxidizing agents cause oxidation but get reduced. And this usually causes people to mix things up every once in a while. Oxidizing agents are the things that are going to make something else get oxidized. I think if you already took Religion 35, you learned about change agents, people that cause change. So an oxidizing agent causes oxidation. Generally, oxidizing agents include metal ions. That's probably the most common type of oxidizing agent that you would see. In most of the examples that you see in the data booklet or in practice questions, the things with positive charges are the oxidizing agents. It could also be non-metal atoms. For example, Cl2 gas is one that shows up once in a while. It would be an oxidizing agent. Now, does anyone want to ask anything about that? So it would be realistic for us to show you something like, well, let's just make one up here real quick. If that was the reaction that was happening, could you identify the oxidizing agent or the reducing agent? Because that'll be the next thing in the reaction. So if you look, I start off with two different elements. One of them is a metal, one of them is a non-metal. The non-metal one should be the oxidizing agent because it should gain electrons to become an ion. Anytime you have an ionic compound, remember that you need to think about it as though it were the two ions that made it up so that you can really see what happened to the electrons. If I look, I see, oh yeah, the chlorine, when becoming chloride atom ions, and now has a negative charge, so it clearly gained some electrons. So this would be your oxidizing agent, and this would be your reducing agent. Everybody's good so far? Okay. then the reducing agent is just the other side of the story. Reducing agents cause reduction of another substance, but actually are the things that are getting oxidized. So there you're looking for metal atoms, and those are probably the most frequent ones. Metals, because we see them in electrolytic cells, voltaic cells. We see them as part of corrosion reactions, but metals are very frequently the reducing agents. Some metal ions. So remember in your data booklet, there are a few things that show up on both sides of the table. I'm going to use Fe2+ as an example. Fe2+ shows up on the reducing agent side over here, but also on the oxidizing agent side down there. Some metal ions could get reduced to form the metal or get oxidized to form a different version of that metal ion. So here we're talking about polyvalent metals, the ones that have more than one possible charge. That's the only scenario where you could see a positive ion getting oxidized, so acting as the reducing agent. Non-metal ions would be things like these guys, all the ones with negative charges. And so they're the ones that give away electrons. They get oxidized. Anybody have anything they want to ask there? Okay. It'll be really important for most questions that you know that there's an identical amount of electrons lost and gained. So a lot of what we did was to make sure that we had the same number of electrons in our reduction half reaction as we did in our oxidation half reaction. And if there weren't the same number, you had to multiply one of the reactions out so that you had the same number of electrons. Now our next big topic was spontaneity. So we're talking about a reasonably short period of time. Spontaneous reactions should show you that something has happened fairly quickly. Usually there are two ways that we could ask you about this. We could ask you about the most spontaneous reactions that are observed with a table something like this one. Now on my table that you see here, I actually identified which are the reducing agents and which ones are the oxidizing agents. But you could expect if it was a diploma, they're not going to tell you that. That's what they're going to ask you. They're going to ask you first to recognize which set of substances are the reducing agents. So from what we saw before, the solid metals should be the reducing agents and the positive ions should be the oxidizing agents. So that should be your first decision. If it was a multiple choice question, they would have the wrong answer be the other category. So if I asked you which ones are the oxidizing agents, A solid, B solid, C solid, D solid, they would be one of the wrong answers so that you for sure had to pick the right category. But then, what is the strongest of them? You do that by counting reactions. So if I look at my oxidizing agents and I look over here at D, D2+ has 3 spontaneous reactions. C2+ only has 2, A has 1, B has 0. So if I were to put these in order from strongest to weakest, I would say D, then C, then A, then B. I would put them in order like that from top to bottom because that mimics the order that I would see in a table of half reactions like the one in your data booklet. I could also finish the reactions off by recognizing that if I'm going to write a reduction half reaction, the solid version is going to be on the other side. So here's my completed table down below. So just like in your data booklet, strongest oxidizing agent at the top, strongest reducing agent at the bottom. Now sometimes instead of a data table, they could give you just a list of reactions. So it could say something like D2 positive plus B solid, and we see that it's spontaneous. Or it could be something like B2 positive plus D solid, and it could say something like no evidence of reaction or not spontaneous. So instead of giving you a chart where you count how many things there are, it could be a list of reactions. One or the other would show up, but I would say it would be unlikely that you'd see both of those because they're both about the same idea. Does anybody want to ask something about the spontaneity idea? Okay. So now that we know about this, if we have the table of reduction half reactions, either in the context of a question, because sometimes they'll do that, they'll give you a table of 3 or 4 reactions as part of the question, or maybe it's in your data booklet, you want to remember the spontaneity rule. If the oxidizing agent is higher than the reducing agent, it's spontaneous, and if those are reversed, it's not spontaneous. That's how you can help determine what's going to happen in a redox reaction, which is what's in the next thing. Does anybody want to ask about that? Okay. So frequently, there'll be a question that asks you, given this set of substances, what's going to happen or what's going to react? Sometimes they'll list a whole bunch of compounds, and you have to remember that you need to split them up. So let's just say you have a mixture that has iron, that has nickel 2 chloride solution, that has, I don't know, silver, and that has sodium chloride solution. For some reason, you decided just to pour these all in the container. Maybe it's the waste container in the lab, and we're just wondering what kind of reaction is happening in that gross bucket that's in the fume hood. So say this is what you had. Remember, anytime you have something that's aqueous, you also have water. Water doesn't frequently take the place of the oxidizing or reducing agent, but it could in some cases. Remember that you also have the 2 ions that are part of any soluble compound. So when you look in your data booklet and you're asking yourself which of those things is the strongest reducing agent, you're going to look not for NiCl2 aqueous, but for Ni2 positive or for Cl negative. Does anybody have anything they want to ask there? Okay. So if you take a look in your data booklet, remember that you can't pick something if you don't have it. I didn't say that I had silver solution. I said I had silver metal. So even though silver is pretty high as an oxidizing agent, I don't have Ag positive ions. I have Ag solid. That's a pretty common mistake that happens too, where you pick something that you don't actually have. So if we scan down this list, it should be nickel, but you have Ni2+. It can act as an oxidizing agent. Sodium could also act as an oxidizing agent. Water could act as an oxidizing agent, but if you check their position in the data booklet, nickel is the highest, so it is it. That's going to be my oxidizing agent out of the stuff that I have there. If I look at some of the other things, this can be a reducing agent, so can this, so can this, and I already had the chloride ions there. So when I look, I'm going to see which of them is the lowest. So silver, I said, was on the reducing agent side, but it's really high. Water is even higher. Chloride is even higher than that. So those ones were all pretty high. But if you look down near the bottom, there's Fe solid. It is the one that's lowest, so it's going to be my reducing agent. A lot of the time, this principle is what you have to apply to an electrolytic or voltaic cell. Like they'll show you a picture of a cell with all of the substances, and then you do this exact procedure to figure out which thing is the oxidizing and reducing agent so that you know which one is at the cathode and which one is at the anode. So if this is what we were doing, we would have the nickel reaction, and we would have the iron reaction, like this. Since they both have 2 electrons, I don't have to do anything else because it's the same. I can just add them up and make one overall reaction. And I would definitely say that this one is spontaneous because my oxidizing agent was higher than my reducing agent. Everybody's good? Okay. So we did a redox titration, and the one that we used was MnO4, which is permanganate. Now, in case you forget what color permanganate is at the back. It's in this list of things that has colors. So is dichromate. It's not one that we used, but if you could look up its color here. What you should recognize is that these things, when they're reduced, change color. And if you forget any of the colors, all four of these things are in the table at the back where you could look up what color they actually are. So memorizing the color is not something you need to do, but recognizing when all of this finally gets reduced, the color changes. When all of the Cr2O7, so the dichromate ion, gets reduced, the color changes. Did you guys want to ask anything about that? Okay, so just in general for titrations, and you see it again later, you should be able to identify what the titrant is. You should be able to identify what the sample is. You should be able to calculate concentration or to manipulate that formula to say find the volume or find the number of moles. The basic steps would be find the moles for something that's known, use the mole ratio between the thing that you know and the thing that you're looking for, and then calculate your final answer, whatever that is, usually volume or concentration. Other things for titrations, you got to remember that you got to be within 0.2 milliliters for a trial to be counted as part of the data. Do you guys have any titration questions that you want to ask? Yeah. In the burette, yeah. So if we imagine the picture, here's our burette. This is where the titrant goes. And then underneath, we generally have an Erlenmeyer flask into which we've put the sample. And generally, we used a pipette to measure the sample. So those little things with the clicker on it where you roll it up until there's 10 milliliters, that's how you measure out, because you want to make sure you have exactly 10 milliliters of your sample. To put stuff into the burette, you don't have to measure it because the burette itself has the graduations for measuring. So the thing that the one that I started with, because I know its concentration and volume, I'm going to figure out how many moles I have of it. That's the one that I know. It always goes on the bottom. And I get the mole ratio from the balanced reaction. Anybody else want to ask a titration question? Okay. There's going to be a titration question somewhere on the diploma, maybe this unit, maybe the acid-base unit, maybe both. Sometimes the question is to calculate something. Sometimes, though, it's as basic as, do you know the setup of a titration? Do you know what you're looking for in a titration? Could you figure out which thing is the titrant and which thing is the sample? So it doesn't have to be a calculation. It could be something basic about the setup of it. Okay. Next thing, oxidation state, which leads us to oxidation numbers. Oxidation state is the net charge that it would have if it had all of the electrons. And so we assign oxidation numbers to represent that. So those are the rules for oxidation numbers. Elements always have 0 as their number. Hydrogen is +1 except metal hydride. So for example, something like that, where there's a metal first and then hydrogen in the compound. Oxygen is -2 except in peroxides like H2O2, where it's -1. Any kind of ion that has one atom, so something like Cl- or Na+, that's a monoatomic ion, always have the same number as their actual charge. So if you have an ionic compound, look at what the charges of those two things are supposed to be, and that's their oxidation number. All the other oxidation numbers you have to figure out. The sum in anything that's neutral has to be 0. The sum in any polyatomic ion has to be its charge. So for example, if I had CH3OH, that's a neutral compound. The oxidation numbers would have to add up to 0. So oxygen is -2. Each of the hydrogens is +1. So +1 here, and then +1 times 3. So if you look at that, I have 4 positives and 2 negatives. So the carbon has to be -2 as well for its oxidation number. Peroxide, H2O2 is the only one you should recognize. Peroxides have oxygen-oxygen single bonds in them, but that's the one you should recognize. It's the only one that would show up. If we're looking at a polyatomic ion, so let's say I'm looking at PO4 3 negative, I know that each oxygen is -2, and there are 4 of them. So that gives me -8 total. But I don't want the total to be 0. I want it to be -3. So that means our phosphorus is +5 for its oxidation number. Usually, there is a question somewhere. It's almost always a numeric response question, and it gives you 4 compounds, say, with the same element, and asks you what's the oxidation number in all of these. But oxidation numbers can be really useful just to check and see, did this thing gain or lose electrons? Is it the oxidizing or reducing agent? You could use them to balance, but you don't have to. So if the oxidation number increases, it's been oxidized, so it's the reducing agent. If it decreases, it's been reduced, so it must be the oxidizing agent. Do you guys want to ask anything about oxidation numbers? Oxidizing, reducing agents, anything like that? There's the idea of disproportionation. Disproportionation is where you have the same substance acting as both things. And here are some hints to look for. If there's only one reactant, and if the same atom is in more than one product. Those are not 100% rules, they're just clues that you can look for to help maybe hone in on the one that is disproportionation. Sometimes the same atom will be in more than one product, but that atom is oxygen and it has -2 the entire time. Sometimes there's only one reactant, but what you had was a dissociation reaction, and so it's not actually redox. But those are pretty good hints, especially if they show up together. I would say that's a pretty good hint that it's disproportionation. So in this reaction, this one is the oxidizing agent because this sulfur gets reduced to S8, but also oxidized to HSO4. If you were going to try to balance a disproportionation reaction using the half reactions method, which a lot of people prefer, the best solution would be to write your oxidizing and reducing agent twice, once in each of the reactions. So those would be my initial half reactions that I would use if I was trying to balance this reaction. Do you guys want me to balance this reaction? Let's just do that so we can go over the steps. When you're balancing reactions, the first thing you need to do is balance atoms that aren't oxygen and hydrogen. And if you don't do that, every other step will be wrong, and you'll be very frustrated with yourself. And I know that because it happens to me. So if I look at the first one, I would start by putting a 4 here so that there's 8 sulfurs on both sides. In this one, I would start by putting a 2 here so that there's 2 sulfurs on each side. Second step is oxygen, and you balance oxygen with molecules of water. There's 3 times 4, so 12. So I'm going to add 12 waters on the other side because to balance oxygen, you add molecules of water. In the other one, I have 2 times 4, so that's 8. And then I have 3 on the other side. So I need 5 more on this side. Does anybody want to ask anything about any of those steps so far? Okay. Then you balance hydrogens. So if I look at my top half reaction, I have 4 hydrogens on the left, and then I have 12 times 2, which is 24 on the right. So there's a difference of 20. In my other half reaction, I have 5 times 2, so 10, plus another one, 11. And then I have 2 over here, so there's a difference of 9. Once you do that, then you check the charges to add electrons. So if I look at my top reaction, I have 20 positive charges, 4 negative charges here, and then I have 0 on the other side. So altogether, this is 16 positive charges. So I would need to add 16 electrons to get that down to 0 so that it matched the other side. If I look at the bottom one, on this side, water doesn't have a charge. This one is negative charge, so I have -1 here. Then I have 2 negative charges here, plus 9 positive charges, so altogether 7 positive charges. Your initial instinct might be to add 7 electrons, but remember they have to match both sides. So to get from +7 all the way down to -1, 7 is not enough, you need 8 electrons. Then last step would be to notice that this reaction does not have the same number of electrons as this one. So I would multiply everything in this one by 2. Does anyone want to ask steps about the half reaction balancing method there? Yeah. Oh, you want to do this in a basic solution? Sure. Sure, we can do this in basic. Can I do a simpler one in basic solution? These are big numbers, big numbers. I'm just going to pause. Okay, so let's do a basic one. So how about let's do this, MnO4 negative plus I negative, aqueous goes to MnO4 2 negative plus IO3 negative. Okay, so we'll do this one in, yep, I did that. We'll do this one in basic solution. So similar steps, but we have to do 5 through 8 instead. Oh, I took away my M here. Okay, so first thing, decide what your 2 half reactions are going to be. So MnO4 negative, MnO4 2 negative go together, I negative and IO3 negative go together. The first few steps are the same, so you balance things other than oxygen and hydrogen. So it would be manganese in the top reaction, there's 1 on each side, so we're okay. Iodine in the bottom reaction, 1 on each side, so we're okay. Then we look at oxygen, so there's 4 oxygens on either side in that top reaction, so nothing needs to happen. But on the bottom one, we need 3 waters on the left to balance out those 3 oxygens that are on the right. Once you've done oxygens, then you take a look at hydrogen. Since my top reaction doesn't have hydrogen, I don't have to worry there. My bottom one, though, I have 6 hydrogens here, so I need 6 hydrogens there. Then, this is where the steps are different. If this was acidic, you would go straight to electrons, everything done. But here, we also have to add hydroxide ions in the same quantity on both sides for every hydrogen ion there is. So I would add 6 hydroxides here and 6 hydroxides here. Since I didn't have hydrogen ions in my top reaction, I don't have to add any hydroxides there. Then I combine any place that I have hydrogen and hydroxide into molecules of water. So just on the right in that one, I would do that. Then there's probably water on both sides of that reaction, so I can simplify. So instead of having 3 here and 6 there, I say that overall the net result is 3 on that side, because the 3 on the left would cancel out 3 of the ones on the right. Now it's up to you when you're balancing, but you'll notice I don't erase things, I only cross things out so that I can see what I had written before, just in case. And I think that's a good strategy, especially when you're doing one of these big balancing things. Once I've done all of those simplifications, then I go on to electrons. So I would need an electron on the left. Why? Because the charge is 2 negative there, but only 1 negative on the other side. In this one, I have 6 negatives here, plus another one. So I have negative 7 on this side, and then I have negative 1 over here. So if I'm asking myself what I need to add in terms of electrons, I need to add 6 electrons. That means I need to take this whole top reaction and multiply it by 6 before I add them together. Do you guys want to ask any questions about half reaction balancing? Yeah? Mm-hmm. On one side, they should. So on the side where the hydrogens were, they should cancel out, but you're going to add the hydroxides on both sides, so the other side, they shouldn't. Yeah. Anybody else want to ask anything there? Okay. Okay, so that takes us into sort of the second half of the unit where we started talking about voltaic and electrolytic cells. Electrochemical is the general term for both of them. So sometimes questions will specifically just call it an electrochemical cell because they don't want to tell you if it's voltaic or electrolytic. Maybe they want to ask you that, or that's part of the question. You need 2 or more cells linked together. 2 is always what we looked at. In real life, they could have more, but 2 is what you would have to see. If we're talking voltaic cells, they spontaneously produce electricity if conductors, so my electrodes are placed into a conducting solution. You have an electrode as a solid conductor. It needs to be made out of metal, and you'll see a bit later on, I mentioned this, but I'll just mention it now, that you can have inert electrodes. So the electrode doesn't have to be part of the reaction. Frequently it is, but in some scenarios, the electrode is just there to conduct electricity, but it's not actually participating in the reaction. You always have an electrolyte. So if you look at each half of the cell, there's usually a different electrolyte on each side. It's something that's aqueous. In real batteries, it's often not a solution, but rather a paste. But as long as it's moist, that will work. There's the cathode, the positive electrode. Electrons travel toward the cathode always, all the time, even in the other kind of cell. Electrons always to the cathode. And the electrons go through an external circuit. So sometimes they'll give you pictures of a voltaic cell or an electrolytic cell with numbers on them. So I'm just going to quickly sketch something here. So here's your basic setup, and they'll give you things like 1, 2, or 3, or 4. Never put the electrons down in the solution. That's not where they are. The electrons are always going in the external circuit, so the wire that goes across the top. Yes, so the cathode, because that's where reduction is taking place, that is where your oxidizing agent will react. The anode is the negative electrode. Electrons travel away from the anode. Oxidation happens there, so it's the reducing agent. Yep. Yep. So when we're in our salt bridge or our porous barrier, or whatever's happening up here, anions always go to the anode. and cations go to the cathode. So look at the beginnings of the word, and that'll tell you where they go. Yeah. The external circuit. And so the electrons are like they can travel through that metal conductor in the external circuit, but down in the solution, that's where your anions and cations are moving around. Right. And so the electrons are going out in the external circuit, and then those charged particles complete it the other way around. Is that what you're asking? Yeah. Right, but it's because of the reaction that's happening, not because of those things in the salt bridge. The things in the salt bridge move mostly because of what's happening at the anode and cathode. If you think about it, the cathode is getting electrons, so the positive thing in the salt bridge is attracted to the electrons. The anode is losing electrons, so the negative thing in the salt bridge is attracted to the positive that's left over there. Anybody else want to ask anything there? Now this next little bit, maybe you'll remember this. It was like lesson 16. We did a big table where I just made you look at a whole bunch of different types of cells that exist. You don't have to have memorized the definitions or like the reactants and products of a specific cell, but it would be fair game for them or me on a test like I did to show you a battery that you haven't seen before and then describe it to you and ask you, what's the cathode, what's the anode, what's happening, what reaction is taking place here. So just remember that there are different kinds of cells. Fuel cells have been showing up frequently lately, maybe because fuel cells are some big new thing, because hydrogen fuel cells could maybe power cars, maybe that's a big deal. But they're still just an electrochemical cell. They still have the same things, an anode, a cathode. The cathode is still where reduction is happening. Electrons always flow towards the cathode. So whatever actual battery or cell they give you, all of those points are still true in that context. Now, if we're thinking about standard stuff, like what we built in the lab, you would have an electrode and an electrolyte within its own container. So our standard picture of two beakers with something metal sticking inside of them. You need a porous boundary, so it can be the salt bridge or it can be the ceramic cup. So Ireland en français, cloison poreuse or barrière poreuse is what you would see. Does anyone want to ask anything? But we kind of covered that a bit at the beginning. Okay. So you might run into some cell notation. Please remember that anode comes first and cathode comes second. There was a question on one of the mocks that just showed you cell notation and asked you what's the reduction half reaction, but to know that you had to recognize that the cathode is the second part. Even if you're not sure, look them up in your data booklet, because hopefully if you do that, you'll recognize right away, oh yeah, this thing's way up here, so this thing has to be the cathode. Mm-hmm. You were allowed to write anything that you feel like writing anywhere on the diploma except the answer sheet. So same thing that applies during our tests. You can draw things, sketch things out, and I would recommend doing that if you think it's going to help you answer the question. Yes, data, like everything that you have except for that bubble sheet where they don't only want you to put the bubbles on, you can write things. So what might be a good idea is on your data sheet, like add some notes to yourself even before you start so that when you get to the question, you're like, yeah, I know these are oxidizing agents. I know these are reducing agents. Okay. So here's a pretty typical standard cell with zinc and copper with a picture on it. It's the same picture that I showed you in your notes. So I just want to kind of come down here, especially for this section, this observation thing. Frequent observations are that the cathode increases in mass and the anode decreases. That doesn't have to happen all the time, but in a lot of cases, especially when you're dealing with metals, those are some pretty common observations that you'll make. Color is something that you will frequently observe. So in this one, zinc didn't really have a color, but copper did. Since, in this case, copper ions are being reduced to copper metal, the color becomes less intense, but it could be more intense in a different scenario. So whether the color gets less or more intense depends on the actual electrochemical cell that you're looking at. If the zinc had a color, its color would get more intense because it's getting oxidized and I'm making more of those zinc ions. Other things are the movement of the ions in the salt bridge, which we mentioned before, and the movement of the electrons. In this one, though, it doesn't have them, but always check, are there bubbles? Is the pH changing? Is there some sort of precipitate that's forming? Because sometimes that will give you a hint as to what kind of reaction is happening. So if the question tells you that you see bubbles forming in one of your half cells, you know that there's a gas. And so you can check to see, okay, would it be oxidation or reduction if this gas was forming? So aside from color and mass, those are a couple of other things that you can look for. Do you guys want to ask anything about that? Okay, so here's the inert electrodes. So if you see carbon or platinum as an electrode, it means it's not participating in the reaction, which means everything that you need for the reaction would be in the electrolyte instead of in the electrode. And if you were writing the cell notation, you would still write these as the cathode or anode. They're just not participating in the reaction. Do you guys have questions about inert electrodes? Yeah. Yeah, so this could be the scenario, say, where you have, we'll just put platinum here and carbon here, and everything that's actually reacting is in solution. So maybe on this side, it's my MnO4, my permanganate, and on this side, maybe it's like Fe2 plus ions, where nothing solid is actually part of the reaction. That's what we did in our titration, was those two things, so we didn't even have a solid that was reacting. Anybody else want to ask anything there? Okay. Moving on, reduction potential. So those are the numbers in your data booklet where it says electrical potential measured in volts along the side. If you have a voltaic cell, the cathode will always have a greater potential. If we're looking for standard reduction potential, it's listed in your data booklet. And hydrogen was the reference cell, meaning it's the one that was given the 0. Okay? Now, if we're looking for the potential of a cell, it should be cathode minus anode. Voltaic should be positive. Electrolytic should be a negative number, and sometimes that can knock out 2 multiple choice answers if you know that principle. Does anyone have questions about cell potential? Frequently, it's a numeric response question. Frequently, not all the time, but frequently it's numeric response. So just remember when you're doing this, you're frequently going to be subtracting a negative. So if I'm looking at my copper zinc cell, copper's is positive 0.34 and zinc's is negative 0.76. So remember, when you subtract a negative, it's like you're adding it. That's why it gets bigger. So just don't forget that, or don't forget that there's 2 negatives, because you might end up with the wrong number if you don't do that. Now the other part of this is that the reference half cell is totally arbitrary. The fact that hydrogen has the 0 is, I think, in this one, because it means half of them are above and half of them are below. So we could pick anything and give it 0. All of the individual values would change, but relative differences would remain the same. So on one of those mock diplomas, that was one of the questions. What would happen if we chose something else as the reference half cell? If I was looking at that copper zinc cell, the potential would still be positive 1.10 volts. The space between them hasn't changed, just their actual numbers have changed. Okay, so relative distance stays the same. And You never multiply it. Hess's law usually messes people up and makes them think they always need to multiply everything. But this number, if you're going to multiply the reaction by, say, 3 to get more electrons, you would not multiply the volts by 3. It stays the same. Anybody? Yeah. Mm-hmm. Voltaic or electrolytic could have inert electrolytes or electrodes. It doesn't matter which type. So I'm just going to scroll back up here. This doesn't have to be a voltaic cell up here for it to have inert electrodes. Frequently, though, electrolytic cells will have inert electrodes, but it's not like a rule. It's not a rule that one has them and the other one doesn't. Correct. Electrolytic cells are non-spontaneous reactions. So if I had an electrolytic cell, often an electrolytic cell has my two little things here. Sometimes it's even one solution with my two electrodes in it. Sometimes it's two solutions. But my electrolytic cell has to have a source right here. So look at the picture, and sometimes that's the thing that you need. If there's a V, it means there's a voltmeter, and it's voltaic. If there's a source or a battery, then it means it's electrolytic. The only time they won't tell you what that piece is if that's the point of the question, is to figure out which type it is. Yeah, like if they don't tell you that that's a source, they would tell you some other bit of evidence that would lead you to believe that it was an electrolytic cell. So if they don't tell you there's a source, maybe they'll tell you it's not spontaneous. Or maybe they'll tell you, hey, these are the substances that are reacting and this is the one that's getting oxidized, and you'll look in the data booklet and say, oh, well, my oxidizing agent is lower than my reducing agent. So there will be something that would have to tell you which type it is. Otherwise, you might not know what would go there. So oxidizing agent and reducing agent are still, so if I'm looking at my oxidizing agents, they're strong this way, and if I'm looking at my reducing agents, they're strong that way. I still want to pick the highest oxidizing agent and the lowest reducing agent. So that rule doesn't change, but in an electrolytic cell, my highest oxidizing agent will be lower than my lowest reducing agent. Anybody else want to ask anything there? I know maybe it's counterintuitive. People think that they have to do the opposite, pick like the highest reducing agent and the lowest oxidizing agent. Never do that. Always pick the strongest one all the time. Okay. So corrosion is an example of redox happening where we kind of don't want it to. It's any metal with oxygen and water. So in your data booklet, there's a reaction where oxygen and water are the oxidizing agents. What's up, bud? And so in corrosion, that would always be the scenario. The oxygen and water would be the oxidizing agent, and the metal would be the reducing agent. So when we're thinking about corrosion, sometimes you get a protective layer. So I usually show a picture of copper oxidized. I'm sure you've all seen it. It looks green when it's oxidized, and it actually protects the other copper that's underneath. But iron doesn't do that. It flakes away, so you need to protect iron. So we went over some ways that you could protect iron from corrosion. Any sort of barrier, which is what paint would be, would work. So it might not prevent it completely, but it'll certainly slow it down. So painting it, covering it with something that will not let water go through, so like any sort of oil or lubricant or thing like that would work. Sometimes the barrier will be another metal. So covering the metal that you're trying to protect with something else that won't corrode as easily, or that if it does corrode will form that protective layer. Or sacrificial anodes, like magnesium or aluminum. So those are your basic ways. If we're talking about iron, there's a specific process called galvanization, where you cover the iron with zinc. The zinc does two things. it reacts easier than iron, and it forms that protective barrier that doesn't flake away. Sacrificial anodes are strong reducing agents. If you're trying to find a sacrificial anode, you need to pick a stronger reducing agent than the thing you're trying to protect. That's why magnesium and aluminum make good choices, because they are really strong reducing agents. So here's my question. If you look at your data booklet, sodium, solid sodium, is a stronger reducing agent than both of them, but I'm not going to pick it. Can you please tell me why? Yes. Sodium plus water equals giant explosion and lake. Everybody remembers that video? Yes. Okay, good. So using a sacrificial anode will protect the iron. That means it will react instead of the iron. On one of those mock diplomas, there was that question with the indicator that could be blue or pink, and you had to determine whether just the oxygen and water were going to react or whether the iron was going to react as well. Okay, now we're down into our non-spontaneous things. So these are our electrolytic cells. Electrolysis is the process that's happening in the electrolytic cells. They have electrodes and electrolyte, but they absolutely have to have an external power source. So a lot of things are the same. Oxidizing agent still reduced, reducing agent still oxidized. Oxidation still happens at the anode, reduction still happens at the cathode. And if we're thinking of our power source, the cathode has to be attached to the negative side of it where the electrons are coming from. So if we're looking at a battery, we want the side that the electrons are on. Now, electrolysis is used for producing elements, metal refining, and electroplating. And I would say electroplating is the one that comes up the most often. Like, I want to plate my spoon with gold. I want to plate this particular bowl with silver. So I want to cover some other metal with a thin layer of the one that's there. Anytime we're doing electrolysis, remember that there's this idea of over potential, where you actually need a little bit more than what it says. So if you think about Unit A, potential energy diagrams, we would always draw them like this, where this is the activation energy. Activation energy is kind of the same idea. Even though that's an exothermic reaction, I actually needed a bit of energy to get it going. Same thing with these electrolytic cells. You actually need a little bit more electricity than it says to get over that initial hump. Because of that, we have this chloride anomaly, because water has a bigger overvoltage or overpotential. So if you look in your data booklet, chloride is high up here and water is a few spaces lower. On the reducing agent side, that says water is a better reducing agent than those chloride ions. And so, like it says here, it should be the thing that gets oxidized, but chloride is actually oxidized first. I'm just gonna, that's a point in the curriculum. That's not like a fun little side note. That's like an objective that is probably gonna get tested. And the best way for them to test that objective is to give you a solution and ask you what is the oxidation half reaction that's going to happen, and let you choose from water, chloride, or a few other things that are in the solution. So just make sure you always pick chloride ions over water. Okay. Do you guys want to ask anything here? Yeah. The chloride ion and water? Yeah, so water could actually be both, but in this context, we're talking about them both as reducing agents. Anybody else want to ask anything there? Okay. Sort of the last thing we did then was the Faraday stuff. So here's the formula. People sometimes have trouble remembering that formula, so maybe it can be one of the things that you jot down on your data booklet, like Avery was suggesting, like you can write things in your data booklet. The Faraday constant is in your data booklet on page 3. I had someone tell me when they were doing their mock diploma they couldn't remember what F was, and it's in your data booklet, page 3. Same place that you would find kW, all of the heat capacities, the prefixes like kilo and mega and all of that stuff so that you know what they mean. So we're calculating the amount of electrons, and then we can compare that stoichiometrically to the thing that we're talking about. So very often the context is some kind of metal in its ionic state with some kind of positive charge. Whatever the positive charge is of the metal, that's how many electrons there would be. So if this was 3 positive, there would be 3 electrons in that reaction. So if I was trying to calculate something about this particular mystery metal with a charge of +3, I would use the Faraday thing first. Then I would take that and use the mole ratio. The mole ratio would always have the thing that you want on top and the thing that you already know on the bottom. So in most cases, you would start a Faraday question by calculating the number of moles of electrons. Then you would multiply it by the 1 mole of metal, and in this case, over the 3 moles of electrons. That would tell you how many moles of metal you have, and then usually what you're doing is calculating the mass of metal that you could plate in a particular time with a particular current. That's generally the setup. They could ask you the question in the other order. They could say, I want to plate 25 grams of silver onto this spoon. How long will it take me? In which case, you would work backwards, but you would have to look at your ratio and probably do it the other way around. So if you start with electrons, they go on the bottom in the ratio. If you start with the metal and you're trying to find out something from Faraday's formula, your ratio would flip over, and it would be 3 on the top and 1 on the bottom. Okay? Now that is everything that I have. So in this formula, I is the current, and it's measured in amps. T is time in seconds. F is the Faraday constant over here. This is moles of electrons. And just remember, I forget which class it was the other day, but I said that there were 30 seconds in every minute for some fun reason, but there are 60 seconds in 1 minute and 60 minutes in 1 hour. Usually minutes is as far as they make you convert, but it could be hours potentially. Anything else you guys wanted to ask there? Current multiplied by time. No, current multiplied by time is coulombs. Yeah, it's this C up here. So this multiplied by time, because current is coulombs per second, so that gets rid of the second, and then the Faraday constant gets rid of the coulombs and just leaves you with moles. Anybody else want to ask anything there? Okay.